This is a picture of the planet Uranus. It was taken by Voyager 2 in 1986. Since then, our only views of the planet have been through this iconic photo and Hubble's sharper but still distant view. So what do we see? Well, the planet is surrounded by a thin ring of haze that obscures the details of its atmosphere. But what's strange is that when we look at it with Hubble, sometimes this haze disappears. So where does it go? There are several competing models for how Uranus' atmosphere works. The most straightforward one is that it behaves like our own, where the sun heats the surface, which radiates the heat back out into space. This model predicts that the heat should be redistributed pretty evenly around the planet. But the problem is that this doesn't match observations. The atmospheric temperatures vary wildly around the planet. These dark spots are over 200 degrees Celsius colder than the surrounding areas. So we know there has to be another explanation for how the heat is distributed. One of the other models is that the atmosphere is layered, and some of these layers absorb visible light and re-emit it as heat. So sunlight hits an upper layer, heats up and then radiates the heat down into lower layers, which can be opaque and reflect the light back into space. In this way, you get a redistribution of heat from the top to the bottom of the atmosphere, even though the sun is only shining on the top layer. And it also explains why we see dark spots. They're dark because they're opaque and reflecting the light back out into space. And because they're opaque, they're also very cold. But if this model is true, then the atmosphere should always be hazy, because the upper layer should always be absorbing the sunlight and re-emitting it as heat. But Hubble shows us that the haze disappears during certain seasons. So is this just a seasonal change in the atmosphere? Maybe. One idea is that the temperature of Uranus' atmosphere changes significantly from season to season, going from very cold to much warmer. And depending on how warm it gets, it could either cause all of the haze particles to either evaporate or condense. But there's another explanation. Another model suggests that the haze consists of two separate layers. An upper one that's always present, and a lower one that appears and disappears seasonally. The upper one is responsible for absorbing the sunlight and redistributing the heat, while the lower one is instead responsible for scattering the light and making the atmosphere hazy. And so if the lower layer is the one that's seasonally variable, that would explain why we don't always see it. But why would this layer appear and disappear? Well, as it turns out, the chemistry that forms these particles is really sensitive to the amount of sunlight it receives. You see, the molecules that make up this haze are called hydrocarbons. They're made up of hydrogen and carbon atoms. But on Uranus, these atoms aren't found freely floating around. Instead, they're locked up inside larger molecules like methane. Methane is an incredibly stable molecule. It takes over 200 degrees Celsius to break it apart into its constituent hydrogen and carbon atoms. Once these atoms are free, they can react with each other and with other molecules like nitrogen to form longer chains and rings of molecules. These are the hydrocarbons that make up the haze. But if too much methane is present, these atoms can't react with each other and no haze particles form at all. On Earth we have a similar problem. Water vapor in our atmosphere condenses into clouds when it reaches saturation. Similarly, when the atmosphere of Uranus is saturated with methane, no haze particles can form. So this may be what happens in summer. The atmosphere is heated and the methane evaporates, allowing the haze particles to form, and so the atmosphere becomes hazy again. We can test this model by looking for methane in Uranus' atmosphere. We know it exists on Uranus because methane is one of the few things that can absorb visible light and reflect it back out into space. That's why Uranus is blue. So if we observe Uranus when the haze is absent, we should see a strong signal from the methane. And if we observe it when the haze is present, we should see a weaker signal because the haze is absorbing the light before it reaches the methane. And when Voyager 2 visited Uranus, it did find methane in the atmosphere, but it didn't detect any seasonal variation in it. However, scientists think the signal was too weak, because Voyager 2 arrived at Uranus in the middle of winter, so the atmosphere wasn't hazy when it got there. Instead, Scientists have inferred the presence of these seasonal changes by studying the atmospheric temperature. They observed that the atmosphere of Uranus has significant variations in temperature throughout the day and across seasons. In summer, the temperature of the stratosphere is about 70 degrees Celsius, while in winter it's closer to -60 degrees Celsius. And we know that the swings in temperature are related to the formation and evaporation of the haze, because the temperature variations only occur in the upper atmosphere and not in the lower atmosphere. And since we know that the swings in temperature are caused by the condensation and evaporation of haze particles, that means the haze must also be condensing and evaporating in response to the temperature changes. But why are the temperature changes so extreme? If the upper atmosphere is redistributing heat to the lower atmosphere, then why doesn't the heat just spread out and reach a steady temperature throughout? Well, one reason is that the atmosphere is stratified, meaning that there are distinct layers of gases and particles with different properties and they do not mix easily. For example, the swing in temperature only occurs above the 80th parallel. Below that, the atmosphere stays relatively warm throughout the year, and there is any significant variation in temperature from day to night. And this is because there's a particular atmospheric layer called the troposphere, which is the lowest layer of the atmosphere, where all of the variation happens. Below the troposphere, the atmosphere is fairly uniform and static, so the heat produced in the upper atmosphere can't travel down into the lower atmosphere. This might be because the upper and lower atmosphere are divided by a boundary called the tropopause, which prevents the mixing of gases between the two regions. And what's strange is that this seems to be an unexpected property of Uranus's atmosphere. Scientists originally expected the atmosphere to behave like our own, where there are no barriers stopping the heat from reaching the lower atmosphere. So it looks like Uranus' atmosphere is more stratified and dynamic than we thought. But there's still a lot that we don't understand about it. For example, we still don't know exactly what causes the haze to disappear. It could be due to the swings in temperature, or it could be due to something else entirely. So this is an area of active research, and scientists are eager to learn more. If you want to know more about Uranus, I've linked to a video that answers the question, how does Uranus rotate in its side? Thanks for watching.